Alright, so in this video I'm going to be explaining another important article, but this time we are combining continual learning paradigm with domain generalization. So this paper in 2023 is very important in ICLR 2023. In real-world applications, deep learning models often run in non-stationary environments where the target data distribution continually shifts over time. There have been numerous domain adaptation methods in both online and offline modes to improve cross-domain adaptation ability. However, these domain adaptation methods typically only provide good performance after a long period of adaptation and perform poorly on new domains before and during adaptation in what we call the unfamiliar period, especially when the domain shifts happen suddenly and significantly. On the other hand, domain generalization methods have been proposed to improve the domain generalization ability on unadapted domains. However, existing domain generalization works are ineffective for continually changing domains due to severe, for example, catastrophic forgetting that I've explained for playlist for continual learning is very important. When the episode comes, you may forget the early episode. So continual learning always tries to do some kind of start regularization to make sure that their weights is the distance between the weight and the prior episode or previous task is less than a threshold, this distance, to make sure that we don't the flexibility is not too much. So there is a trade-off between stability and flexibility. They call it stability-flexibility dilemma in neuroscience. So to overcome these limitations of domain adaptation, domain generalization in handling the unfamiliar period domain during continual domain shift, we propose this model, which is a framework that focuses on improving models' target domain generalization capability, while also achieving effective target domain adaptation capability right after training on certain domains and forgetting alleviation capability on past domains. And it includes a training-free data augmentation module to prepare data for TDG. A novel pseudo-labeling mechanism to provide reliable supervision for target domain adaptation, and a prototype contrastive alignment algorithm to align different domains for achieving them. I have a playlist for contrastive learning that is very important. So this is an overview of applying our framework for continual domain shift learning. First, it starts with the label source domain, applies rand mix on the full set of source data to generate augmentation data, and uses a simplified version of PCA for model optimization. Then for continually arriving target domains, it uses T2PL to generate pseudo labels for all unlabeled samples. So we have a feature extractor here and here, but here is for source domain, then here is for first target domain, second target domain, etc. The other thing is that we have labeled samples for source domain, but unlabeled for target. Then in the target, we have pseudo label samples because we don't have label. But they use for source domain, they use rand mix, and then after adaptation, they give it to classifier. So this is classic. But here, after classifier, they give it to PCA. And so the methodology is like this. We first formulate the problem of continual domain shift learning and introduce the three major modules. So we assume that there is a label source domain set. The TIS domain contains this number of data samples, and all target domains share the same label space with the source domain. Note that the domain order is randomly determined, which means that the superscript does not always indicate the same domain. Then we have random mix-up augmentation. At the beginning, only a label source domain is available, thus we face a pure single domain generalization problem where the model is trained on a single domain and tested on the other unseen domains. So RandMix relies on N augmentation simple autoencoders, where each autoencoder consists of an encoder and a decoder. We want RandMix to be as simple as possible, preferably to be without training. Inspired by this interesting article, the encoder and the decoder are implemented as a convolutional layer and a transport convolutional layer. With such implementation, even if the parameters are randomly initialized from a normalized distribution, the autoencoder can still generate a reasonable augmented data. So to do more randomness, we inject noise to the autoencoder. We can apply this ADAIN, and they use the ADAIN. It contains two linear layers that are fed with a certain noisy input drawn from this normalized distribution. They can produce two corresponding noisy outputs with smaller variances. So, for example, they blindly pushing augmentation data away from the original possibly hurts the model generalization ability, and injecting randomness with a small variance is a better solution. The two noisy outputs are injected to the representation of the autoencoder as multiplicative and additive noises. So L-in represents element-wise normalization layer here. And RandMix works as feeding training data to all autoencoders and mixing the output with random weights drawn from a normalized distribution. Finally, the mixture is scaled by a sigmoid function. In mini-batch training, every time there is a new data batch, parameters of autoencoders, these noisy inputs and mix of weights are initialized again. With RandMix, we can generate augmentation data with the same label corresponding to all label samples from the source domain. This is just a technical thing, but the pseudo labeling is important, and we can compute the cosine similarity between these centroids and representations of all current labeled data and select top half set of samples that have much higher similarity to the centroids than the rest for each class. Then we use F prime to feed a k nearest neighbor classifier and assign the pseudo label like this. Note that k nearest neighbor, can decentralize the risk misclassification in assigning pseudo labels by a single comparison between class centroids and data samples. And finally, they use these cross-entropy laws. We have prototypes, and here you can see that when the model encounters a domain whose prototype are far from the optimal ones in A domain alignment with regular prototype will enlarge the adaptivity gap. But in B, because rand mix may be helpful to reduce the gap in many cases. In C, in some cases, rand mix may produce a low quality data augmentation that negatively affects the regular prototype learning. So you can always look at this adaptivity gap for different cases. Unlike the alignment on regular prototype, we do not sum up and average prototypes of different domains. Instead, we simultaneously maximize the similarities of data samples to prototypes of different domains. Although in practice, we may have prototypes of just 2 domains, since there is only one old model being stored. We also introduce contrastive comparison into domain alignment process that can enhance the distinguishability of different classes and be beneficial for our pseudo-label. The contrastive comparison includes negative pairs of particular sample and samples from other classes. In our case, our prototype contrastive alignment, so it's a prototype contrastive alignment. PCA stands for, not that famous PCA algorithm, it stands for prototype contrastive alignment. So this prototype contrastive alignment, cross entropy for classification of source domains, and then this when we sum all of them, then we get the total loss. This one is the distillation loss, because we also adapt knowledge distillation from the stored old model to the current model. For example, in knowledge distillation, we have a teacher, we have a student. This teacher is usually a very complex model, so we distill it in our teacher model, in our student model, using just, for example, you can use KL divergence between their outputs. So it has many applications. For example, on-device deployment, because if you want to deploy it on your mobile, then your model should be small. Then you don't even need to have an internet, because it's so small that you can fit it into your mobile. So there are many applications. But this distillation here, they just store it because they have a stored old model. Why not using it?